Hello everyone and welcome back to a new video in our modeling, analysis and design of pile foundation. Once again, a reminder that we are still in the theoretical part of this series, and in the end there will be robot videos talking about how to implement piles in Autodesk Robot. Of course, if you are new to this channel or new to this series, please take a look on the playlist I will be linking on the top right that gives you the videos in chronological order. So if you are missing some information, you should check out that video series because it gives you the videos in an order that kind of makes sense. And in today's video, we are going to be talking about Meyerhof's method, which is one of the methods used to calculate the tip bearing capacity of piles. Because as you remember, a pile resists loads by tip bearing capacity and of course skin friction. So with that being said, and without further ado, sit back, relax and enjoy the show. Alright, so let's take a look on Meyerhof's method. On Meyerhof's method, basically the tip bearing capacity in that method will increase based on the embedment length. The embedment length, if you remember, is the length of pile inside the soil that you are considering. Now, why is that the case? Because think about it. When does the bearing capacity fail? The bearing capacity fails when the pile starts moving down into the soil and the soil is unable to resist the pile from moving down. And this is the case for any foundation. If a foundation starts to settle extensively, this is a bearing capacity failure. Now, for a foundation, in this case pile, to go down, it must displace the soil below it. The soil would like to bulge up. Like, look, imagine you have just a small strip of sand and you place your hand firmly on the sand and you push down on the sand. What happens is that the sand will bulge on the two sides here because you are displacing the sand with your hand, meaning that this material must go somewhere and it will bulge on the two sides that you are not pressing on. The same case happens in a pile, difference being that in order for the soil to bulge up, it must resist the entire soil column above it. So that's the reason why the bearing capacity increases with the embedment length, because it is harder for it to bulge up due to the weight of the soil above it. That's the first thing. The second thing is because the deeper you go in soil, the more historical the soil is and the better the compaction is, and that's a general case. There are exceptions, but in general, the deeper you go, the better the soil. This increase is not to infinity. There is a limit depending on the diameter of the pile and the embedment length, and this has been determined on the site, and I will talk about this later. So this unit point resistance doesn't increase beyond a certain limit, and at that certain limit, after that, nothing changes. Now, this limit is given in the books and various references. You can see that the bearing capacity increases to a limit and then just moves on down. This awkward behavior has been confirmed by tests on site, and I will show you the tests during this lecture. For pure sand, I would have QP equals AP QP. Now, what is QP? What is AP? If you checked out the previous lecture, you should note that AP is the area of the pile, including the soil plug, so the enclosed area. QP is the bearing resistance of the soil. It is cohesion multiplied by N cohesion and stress multiplied by N stress. Now, cohesion is not here because we are talking about pure sand, where the cohesion is 0. The factor NQ can be found from charts. Those are like this, for example, or from tables, meaning you give it a certain friction angle and you can get the value of NQ, which would control here because you have pure sand, meaning the cohesion is almost 0 and the friction is high. So you check out your soil friction angle, for example, 25, and you take the NQ value of around 20-ish or something. So that's easily to be done. How were this chart created? Those were created with soil tests and plenty much of soil lab work. Of course, those are also tabulated. For example, for the 25, it seems it's 26. I think I wasn't really looking well. Let me see. Yeah, okay, fine. I am not really the best, by the way. This is a logarithmic scale, so you better be accurate because, for example, here, this is a 20 step, but that is a 200 step. So you better be accurate here. I was a little bit sloppy, and that's why I didn't get the correct value. The upper limit for resistance is this one. You cannot go beyond this limit of resistance. This is basically this limit. This is the limit which you cannot go beyond it. Half PA and Q10 phi. Now, what is PA? PA is the atmospheric pressure at 100 kilonewtons per meter square, NQ is the factor you got, and tan phi is the tangent of the effective soil friction angle. So why is there even a limit on the tip bearing capacity? Well, it's because of tests on site. What has been done in those tests, and this is of course taken from brajamdas' book, it's a test from references. They basically driven a pile 2 meters and then tested it, and then driven another pile, same pile, at 4 meters and tested it, at 6 meters and tested it, and so on. Now, of course, that didn't happen. I think what happened is they're driven at 3 and at 7 maybe. What I'm saying is they have driven piles multiple depths and tested their bearing capacity. And then they plotted their bearing capacity curve with respect to the depth. And you can see that the bearing capacity increases to a limit, to a certain depth, and then just doesn't increase at all. The bearing capacity becomes unaffected by the embedment depth. And you can even see this reflected in the N60 tests. The N60 test is the SPT test. And of course, when you do an SPT test, you will get values, upper values and lower values. We got a range of between 11 and between 5. When we did an SPT test here at depth 9, we got a range between 20 and 10. The idea behind this is that I wanted to see that the SPT test even follows a similar pattern where it increases and then becomes steady. So the idea of increasing up to a limit and then getting steady is something well supported by the evidence and the test in the field. Now, if you have a pile in saturated clay under undrained condition, then you would have QP equals NCCUAP. And before you freak out, what is this? Well, it is the simplification of this equation, because if you have pure clay, then this doesn't exist, and you have AP, C, and C. And of course, C here is the saturated undrained condition, and in this case, phi equals 0. That's why the Q and Q is no longer there, and NC in this case would become 9 as an approximation. So yeah, that's what you do if you have piles in clays. Now, to finalize this tip resistance lecture is, of course, an example. The example here is basically to calculate the tip resistance based on Meyerhof's theory, and you are given the following information. Gamma is 17, the phi is 35, length of pile is 50, and the cross section is so and so. Notice it is a pure sand, so you don't have C. In that case, you go to the step-by-step procedure. The equation for that is the bearing capacity equation subjected to this limit. What is this exactly? This is AP QP, and you know that QP is C and C, Q and Q, but C is 0, and that's why you only have Q and Q. And of course, it must be less than AP Q limit, and Q limit is half atmospheric pressure NQ tan phi. So yeah, you have everything you need. You can just calculate. The area is 0.45 by 0.45, which is this. Using phi, you can find NQ, which is 143, and you can even check this out in the table before. I think at 3.5, it is 143, so that's true. Or you can check out the alignment chart, but don't do a sloppy job like I just did. Try to be a bit accurate, and you get something like this, which is around 140-ish or something. So you get the value from the chart and just calculate. Q is the effective pressure or below the ground, or stress, so it's gamma LB, which is this, and you just calculate. There's nothing to be added here. And notice that the limiting factor is what controls here. So QP is 1014, despite the fact that QP wants to skyrocket to 7,384, you are actually limited to the limit of QP, which is 1014. So that should be the ultimate bearing capacity of that pile. You still have to calculate the friction capacity of that pile, add them together, and then apply a factor of safety. But that's something we will do for later, because we still need to cover the topic of friction before we go on with this. So yeah, that's everything I wanted to talk about today. I have covered Meyerhof's theory for tip bearing capacity. I hope you enjoyed. And with that being said, I want to give a Meyerhof-sized shout out to my dear channel members in the contributor level and the helper level, whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as their support of the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on, especially subscribing because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video. Bye bye.